All right, in this video we're doing the 8.6 day 1 notes. The objective here is to convert between standard form and scientific notation. Standard form is just a number written like we normally know, so something like 8,342. That's your standard form. A number is written in scientific notation when it's represented as the product of a factor and a power of 10. The factor must be greater than or equal to 1 and less than 10. So this is an example of a problem in scientific notation. So it looks similar to what we had the last 2 days, except we can have more than one digit like we had in the last 2 days. So this number here needs to be between 1 and 10, and then you're going to have some kind of power of 10. So for instance, 10 to the negative second. Okay. So this form is called scientific notation. It's a great way of writing really large numbers and really small numbers so that you don't have to include so many zeros when you're writing your problems. We are going to look at writing both large and small numbers in scientific notation. So again, a positive exponent, we're going to think about having numbers greater than 10. A negative exponent, a number between 0 and 1. So in other words, a very small number. And when we have the number 8,600, that's in standard form, and that would be equal to 8.6 times 10 to the third. And we'll talk about how to get that. 0.0024 would be equal to 2.4 times 10 to the negative third. And again, we'll talk about how to get that. But your positive exponents are going to indicate large numbers. Your negative exponents are going to indicate small numbers. Okay, so to look at two examples, we have the number 69 million. We need to have our number between 1 and 10. So that means that the decimal point is going to have to be between the 6 and the 9. So we would have to move the decimal, would have been at the end of the problem. We would have to move it 1, 2, 3, 4, 5, 6, 7 times to get it between the 6 and the 9. So that should say a 7. In B, we have 0.000071. We need our number to be between 1 and 10. So our decimal is going to have to go right between the 7 and the 1 because 7.1 is between 1 and 10. Your decimal would then have had to move 1, 2, 3, 4, 5 times. And so our exponent would be negative 5 because that's a small decimal. And we'll go slowly through the examples on the back side. All right, so we're going to do 6 examples. Our first number, we have 575 million. So again, in scientific notation, we need to have the number between 1 and 10. So in other words, you're going to have one digit and then your decimal point and then the rest of your numbers. So our decimal point is going to have to land here. So we're going to end up with 5.75 times 10 to the something. To find that something, we think about where our decimal was, which is at the end of the problem. And we would need to move it to where we know it needs to belong, the 5.75. So our decimal would have to move 1, 2, 3, 4, 5, 6, 7, 8 times. And it's going to be a positive 8 because this is a large number. Again, positive exponents are going to indicate larger numbers. In the next one, we have 87 billion. So again, our decimal point needs to be after the first digit. So our decimal is going to have to go right after the 8. So we'll have 8.79 times 10 to the something. Again, our decimal would have began at the end of the number. So we need to move it to where we need it to be between the 8 and the 7. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. And again, that'll be a positive 10 because that's a large number. In example 3, we have the number 62,000. Our decimal is going to go between the 6 and the 2 because 6.2 is between 1 and 10. And then we'll have times 10 to the something. Our decimal needs to go from the end of the number to between the 6 and the 2. So it would need to move 1, 2, 3, 4 times. So that would be 6.2 times 10 to the 4th. The next 3 examples are all very small numbers, in other words, our decimals. And so these are all going to have negative exponents. So our decimal is going to have to go between the 9 and the 8 because 9.8 is between 1 and 10. And then we would have times 10 to the something. So again, we need to count how many times the decimal point would move. So 1, 2, 3, 4, 5 times. And because it's a really small number, our exponent would have to be a negative 5. In number 5, our decimal is going to be, again, after that first digit, so 4.6, because that number is between 1 and 10, times 10 to the something. So we need to move our decimal 1, 2, 3, 4 times. And because it's a very small number, that exponent would be negative 4. In the last one, we have to move our decimal many times. So it's going to have to land between the 3 and the 2, because 3.2 is between 1 and 10. So we'd count 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So that exponent would be negative 9. Again, it's negative because that's a very small number. All right, so again, these are all examples of scientific notation. Make sure that every number here is between 1 and 10. So you'll always have one number and then your decimal point. And then again, your small exponent or your negative exponents are going to be for very small numbers. Your positive exponents are going to be for very large numbers.